What's up, everybody? Good morning. How are you? This is Sean Downs, Sean for Science, and today is another great morning to discuss mathematics. Last time we discussed the irreducible representations of SU2, or at least defined them in terms of their allowed spectra of the operators. This time we're going to construct or show you how to construct an explicit representation of SU2 that is useful for a lot of things in the future. So specifically, we're going to construct a simple unitary representation of SU2 using anti-commuting formal variables, sometimes referred to as Grassmann numbers. Okay, this will be a quick one. So let's recall our Chevalley basis for SU2, given in terms of j plus or minus and j3, where the commutation relations of j3 with j plus or minus are plus or minus j plus or minus, and j plus with j minus gives you twice j3. Great. You might also recall the quadratic Casimir operator Q, which we used to help us define the representations, the irreducible representations, and that is given by j plus j minus minus j plus j3 squared minus j3. Whew, okay. Of course, Q, being a quadratic Casimir, commutes with all of the operators j. We parameterize the irreducible representations by some number L in the set of m by 2, where m is some natural number, where Q, of course, in that parameterization is given by L times L plus 1, and m ranges from minus L to L. Okay, great. So now let's consider some formal anti-commuting variables, sometimes called Grassmann numbers, theta. And specifically, we're going to consider the variables theta plus and theta minus. And we're actually going to extend that anti-commutation relationship a little bit in kind of the physics parlance to satisfy kind of an additional algebra, a different kind of algebra, an anti-commutator algebra. Namely, theta plus with theta minus is given by 1, and theta plus or minus with itself is given with 0. So here the curly braces represent anti-commutators, which is to say, you know, an anti-commutator of A and B is given by A, B plus B, A. Anti-commutators are useful for discussing things like Clifford algebras, which hopefully we'll get to in a future video. So now, from this perspective, let's go ahead and claim a representation. Specifically, let J plus or minus be theta plus or minus, and let j3 be given by theta plus, theta minus, plus a constant, some complex number c, which we don't know yet. So the claim is that these operators give us an irreducible representation of SU2, the 2 of SU2, namely with q equal to 3/2 or that parameter L as 1/2. So proof. So the commutator of j3 with j plus explicitly is given by the following. And as you can see, theta plus anti-commutes with itself, which means that theta plus times theta plus is 0. So this algebra simplifies to just theta plus. Good, so that makes sense. Let's check j minus. So j minus is theta minus. Once again, theta minus times theta minus vanishes. Good, and so we're left with minus theta minus. Good, so far the roots are doing great. Now finally, let's compute j plus with j minus. In other words, theta plus with theta minus. So remember, these are anti-commuting numbers, so we plug them into the commutator, and unsurprisingly, we find that that's equal to 2 times theta plus theta minus minus 1. Put differently, the constraint on the constant c that we defined earlier is that c must equal to 1/2. And so that defines our representation of SU2. Now, let's go ahead and compute the quadratic Casimir and see what we get. So plugging all these numbers in, we once again find, using the fact that theta minus is 0, and so on and so forth, we find that, you know, after some simplification, we find that q is equal to 3/2. In other words, L is equal to 1/2. In other words, this will necessarily give us the relevant representation of SU2. Given the parameterization in terms of L, this means that we have m max given by 1/2 and m min given by minus 1/2. So let's go and construct a representation explicitly that has these given eigenvalues. So they can be built by considering the space of all polynomials in the formal variable theta plus. But of course, that space is really boring because theta plus squares to 0. So really what we're looking at is the set of polynomials a theta plus b, where a and b are just some numbers, some complex numbers. So to be more precise, let's consider a basis for this polynomial algebra given by, say, v0, which is just 1, and v1, which is just theta plus. So we act on v0 with j plus, which is serviced by the operator theta plus, and we see, of course, that we get back theta plus. So no surprise there. Acting on it again with another value of j plus, we find 0. It vanishes. So, okay, good. So we have on our irreducible representation, we can bounce back and forth between 1 and theta plus, and then that's it. That's all we can get in either direction. So then this demands that the action of theta minus on V0 be 0. And that might seem kind of ad hoc at this time, and sure, let's define it that way, and therefore we have a consistent representation, and it is. But in the future, we will see how this actually makes a lot of sense. Before we get to that point, let's just note that right now we have two states, the minimum state 1 and the maximum state theta plus. So yes, they sit nicely on the wedge of SU2 right near the bottom as the first non-trivial representation. So in summary, we have used anti-symmetric formal variables theta to define a really simple, easy to remember, easy to kind of take with you portable representation of SU2. So you might naively suspect that you can generalize this to higher dimensional representations of SU2 by considering a higher dimensional algebra of Grassmann numbers. For example, you might consider theta plus I and theta minus j, and their anti-commutator might give you delta I j. But in this case, you'd be wrong. That's not what you need to do. As it turns out, we're going to need to consider tensor products of these representations, and that, given all these issues of symmetry and anti-symmetry that are floating around, it's a little delicate. So we are going to not deal with that today. We're going to deal with it in a later video. So thank you so much for watching. Hopefully this helps you kind of as a useful mnemonic at the very least for constructing representations of SU2. We will see how to generalize these out to all the rest of representations in the near future. So please stay tuned. Have a great day, everybody.